Okay, thank you for inviting me to give this plenary talk here. It's quite an honor. So I would like to start with a nice view, and I have to say it's actually the trash of nano. That's not where we are really doing the science, but it looks beauty, and so you could have a look at the beauty of nature. So I'm coming from Freiburg, and as I noticed, New Delhi is also very old. So let's just give you 2 slides for some information where I'm coming from. So Freiburg was founded in 1120, and the university was founded in 1457. That means it's quite old, but of course I'm in a technical faculty, and at this time you don't have a technical faculty, so the technical faculty is only 25 years old. So we have 11 faculties, and the technical is the 11th. So the technical faculty has 3 different departments: computer science, microsystem engineering, and since 2 years the third institute, which is sustainable engineering. I'm coming from the middle one, from the microsystem engineering part, and I'm there as a chair of nanotechnology. So as was already mentioned here, I have a rather broad interest in nano, and that means you have to look deeply into physics, but also deeply into applications. And if you go to nano, then you are crossing the border of everything, more or less, and you have to think about every step you're doing and how good you can do that. And you have to control yourself in a way, and that means growing nanostructures and then doing nano devices. Out of that means you have to understand what you're doing, and of course if you want to have devices, that also means that you have to think about mass production, doing that on a large scale, and very often that is still a very critical point. Okay, let me start my talk with one famous person, which was Richard Feynman. And that's actually also the point which I'm normally use in lectures for my students, because I think it's so nice to see this statement from 59 of the last century. And Feynman told, "The principle of physics, as far as I can see, do not speak against the possibility of maneuvering things atom by atom. The problems of chemistry and biology can be greatly helped if our ability to see what we are doing and to do things on an atomic level is ultimately developed, a development which I think cannot be avoided." And the interesting point is we are just at this point. We can do that now, we can think that now, we can understand that now, and that is for me the fascinating point of nanotechnology, of nanomaterials, that we are at this level. But if we go to this level, and if we are decreasing the size of materials, decreasing materials dimension, what you also have to keep in mind that is, you see this graph, it's a simple calculation. We calculated the ratio of surface to volume ratio for different kind of objects like quantum dots or nanoparticles, for nanowires, for nanobelts. And what you see, if you stay above 100 nanometer, everything is okay. If you go to 50 nanometer, you already have an increase of the surface ratio. If you go below 20 nanometer, then surface might take over. What you have there is an increasing effect of the statistic. You have increasing possibility to have defects which affecting what you're doing. Just to give you an idea, silicon has 4 bonds. If you put it on the surface, one of these bonds is broken. You have to kind of maybe saturate that by something. So you can do that in a way. And with increasing size, decreasing size, everything gets more into a struggle of statistic effects. Just to give you an example, a macroscopic cube of with 10 to the 24 atoms has 10 to the 8 surface, 10 to the 16 edge, and so on. If you go to a cluster which has only 1,000 atoms, and that is a cluster of between 2 and 3 nanometer, then already every 10th atom is a surface atom, and every 100th an edge atom if you have a crystal structure. And another idea to just give you how small we are going and what might be the problem you're forcing for that is simply think you want to do a lithography step and you have a deviation of 5%. If you do it in a micrometer scale, then nothing is really 50 nanometers is not what you care for, but if you do it with something like 10 nanometer structure, then 5% of a deviation means 0.5 nanometer, and that means one atom on each side. And that could actually already change the quantum luminescence of your materials. Okay, so how can we grow nanostructures? There are different methods to grow nanostructures, quantum dots, quantum walls, nanowires. The chemist prefers the liquid methods, that means the colloid methods, and then what you're doing is you grow that in a colloid, in a suspension, in a solution under Hunger condition, controls the temperature, Oswald ripening, and so on. I just would like to state out what you see here is that there was already a Nobel Prize. Oh, that was, I think I shouldn't take the mouse. What you see here, there was already a Nobel Prize in 1925 awarded to Richard Zsigmondy for colloid materials, and that is something the chemists are doing now, of course, on a much smaller scale, because at this time, of course, you were not able to see them. There's a lot of, I will not talk about the liquid nanostructures, which we also do a little bit in my group, but I will concentrate on the physics way. That means using CVD process for these nanowires or for these nanostructures. And then you have to ask yourself, should I do it top down or should I do it bottom up? Self-organized, what kind of lithography step I would like to take. Can I do it on large scale, on 4-inch wafers? For instance, can I do it in cost efficient? And of course, for all these things, you have to think about functionalization. That means putting maybe an atomic layer over your structure, and then about doping for device structures, reliability, long-time stability, and so on. Okay, let me give you an idea how we are able to grow nanowires. The standard approach in literature is called vapor, liquid, solid growth. To give you an idea how that is done, what you do is you prepare a kind of either a gold film in ultra-thin or a kind of gold dots on a surface. You put that then in your CVD system, and then you supply gases at high temperature. And what happens then is that the gold droplet gets liquid, it's fed by the gas, you have an alloy, and then supersaturation, and if you have a supersaturation, then the wire grows. It's like a kid's experiments, taking a glass of water with a lot of salt, and you put something in, and then salt crystals are growing. In a way, it's the same what we are doing here for this nanowire growth. You can play them with the gases to have super lattices. If you play with the temperature, you're changing the growth drastically, and that means you might end up with, instead of a VLS growth, with a VS growth. That means the dot gets solid again, and you get maybe a shell, as you see in image D. So I will show you some examples from that. If you do that in such a CVD system, which is normally a tube furnace, it depends how much money you have. If you have an MOCVD system, it costs $1 million. Not very often people don't have that. If you have a tube furnace and control then these with a quartz tube. You can do it in a rather easy way, but still you have to understand what kind of key parameters are controlling your growth of your nanostructures, and that means think deeply what kind of parameter. I will show you some of these parameters and how they are affecting the growth. Leakage control is very important if you're growing oxide-related materials. You have to also think about substrate, catalyst pattern, and so on. So that's very important. If you want to have this VLS growth, what you need actually, and some people forget that, is you have to have a phase diagram. Coming from material science, you know that. So you have a phase diagram between the metal catalyst, which is gold in this case, and the material you want to alloy, you want to grow out of this alloy, liquid alloy droplet. And if you look in literature, what you will see is that actually an oxide doesn't have such a phase diagram. So if you have such an oxide, which could be zinc oxide or in this case tin oxide, so you have to, I'm going back to this image because I need the tube furnace down there. So what people are doing, because these oxides have a high melting point, and of course your tube, quartz tube would not survive that, so they're playing a trick. They're using zinc powder and puts a lot of carbon, that means graphite, in, and by doing that they are reducing the zinc powder or the tin powder to zinc gas and carbon oxide. And that is the case what you do then, and then you have to feed your droplet. So as you see here, okay, I think I'm not touching it. You see it in the middle image on the right-hand side from you. So you feed the droplet with a tin, and then the question is, at which point should I put the oxide into these structures? Because if you have the oxide, it immediately solidifies because it has no phase diagram. And what you end up is kind of like on water with ice flakes. It's the same thing, and if you have too much oxide, you actually cover the whole cap, and then your growth of the nanowire stops. So you have to control that in a good way. You have to decide at which time to put the oxide in, and that means also the leakage control, because oxide could go also due to leakage into your systems. Okay, let's now look for temperature. And if you want to go to a large-scale growth of nanowires over centimeter range for devices, then you have to control the temperature, and then a one-zone oven will not work. You have to have a good control. So we have here now established in my lab a control of growth over 12 centimeter, but still if you have a gradient of the temperature in this area, then what you're seeing is that the diameter changes and the length changes, so have a good control of the temperature. Okay. The next point which you have to decide is, if you go back to this furnace, is you have to decide what kind of temperature you're evaporating your powder, because that gives you the amount how much powder comes, how much gas comes out. In addition, what could be the temperature of your substrate. All of these parameters are actually influencing what you're growing, and you want to have only the one which is in number B, that means the nanowires, but not all the other structures which you see if you have an not good control of the temperature, because that you cannot really use for devices. Okay. So how can you also control what you also have to think? You have a tube furnace, and a lot of people are reporting you can grow the wire opposite to the flow. You have an inert gas which transports your evaporated clump to your substrate, and by a gas flow you are diluting that. And you have two processes. At high temperature you have diffusion, and diffusion goes also opposite to the flow, and that means you controlling by the flow how much of your gas is coming to the point of your substrate. And you see it here in some simulation done by ANSYS, which is for different flow rates, and in a way you can then control it, that you have it homogeneous distribution of the gas over your substrate in a really good controlled way. Okay, so the next choice you have to do is you want to have a good and perpendicular growth of this nanowire. And as we know from epitaxy, then you have to have a fitting substrate, okay, with a correct crystal, with the correct lattice constant fitting to the materials you are trying to grow there. And you see here two examples. One is an A-plane sapphire sample, and the other is a silicon sample which is overgrown by gallium nitride. Gallium nitride, the lattice constant in C direction fits well to zinc oxide. You would think that also for the A-plane sapphire, but the A-plane sapphire substrates are cutted and polished. And if you have such substrates, you have atomic steps on the surface by the polishing, and that gives a lot of inclined wires, and we don't want to have that. If you want to have separate nanowires and later epitaxial grown in a way to the substrate, so you have to think about this choice of the substrate before. Okay, and now let's move for the methods how to prepare these gold dots on a large scale, how to do that in a way that we are able to do that over centimeter range, not micrometer as you can catch on a cold finger, but really in a well-controlled technology for let's say future devices. So there's a lot of methods in the community. I will only concentrate on these three methods to give you an idea, because they are rather cheap. They enable you to make it on large scale, because I think not all of you will have E-beam. And just to give you an idea, if you calculate to have a dot of maybe 20 nanometer with a space of 400 nanometer on a 4-inch wafer, how much dots you have to prepare with E-beam, it takes a weekend. So forget about it if you not have parallel E-beam system. Okay, yeah, so let's concentrate on that. A very simple method is this, what is called in literature nanosphere lithography. So you can buy polystyrene spheres, very good in a size control. The better the size control of these spheres is, the better is your arrangement later. By changing different sizes, you change the space in between. So you spread them in a spin-on-glass process or sedimenting process on your wafer. Then you do an evaporation through these holes. You get what you see here on the left-hand side. You get this gold pattern. You remove them, if it's polystyrene, simply chemically, and then you have this gold pattern. I would not suggest to use that immediately for growing the nanowires, because you would end up with a lot of small wires coming out. First do an annealing step, and then you have a kind of de-wetting of the surface, and then you can do that, and then you are getting nanowires or pillars depending on the size, and with the size of the spheres you are controlling the size of these, a little bit of these dots. Okay, so the nanowires that's one of the advantages why people are so fascinated for this nanowire growth. They are single crystalline, and they are very often, not in all cases, very often completely defect-free. And you see it here, the lattice is completely without stacking folds. It's really beautiful, and that means you are expecting very good properties for that. So that is one method. Another method would be using laser interference lithography. For that, you need an UV laser. You spread that through a pinhole, widen that, and then make an interference pattern, and then are able to do it in a lithography way on whole wafers, or depending on your system. Again, if you do that, taken into account that your substrate might reflect the laser, and that means you need to take care of that with an anti-reflecting coating. The gold pattern is like you see it here in A. If you do a growth and you see that's an AFM image measured by an AFM tool, what you're seeing, it's not completely spherical, it has different heights. If you start to grow with that, you end up with 3, 4 small wires. To do it in a way that you get one pillar out of these, you have to pre-anneal it again, making this kind of wetting, de-wetting process, and then you can grow that on a large scale. And then what you might see is, and you see it here in the image C, is zinc oxide is growing hexagonal. That means it has a C-axis growth, and of course not each of these pillars, nanowires, are perfect in shape, so it's not, let's say, each of them is has a real hexagon, but there are variation from that. And depending if you go for VS or VLS growth, you might also end up with a deviation from the former size of your catalyst. So you see they are normally bigger than your catalyst pattern was, but you can do that on large scale. So just to give you a glimpse, you can do that, and now you have a tool to actually do devices out of that. Okay, let's move. Of course, if you're doing in nanowires and these nanotechnologies, there's a lot of physics behind, and you need to understand that. I don't want to go into all of the details. I will give you a glimpse of some of the things we are doing to understand about the properties of these nanowires, but I will only give you a glimpse. So let's go from what we have here, thinking about the mechanical properties. And I think that's rather an interesting thing, because you might ask yourself, how stable, how mechanical stable are these nanowires? And to test that, what you can do is you can take single nanowires. These were grown actually randomly, so we didn't pay attention for this experiment. We just wanted to have them spread over a large area in a distance. And to just give you an idea, we have an SEM, a tip inside, and so and then you kind of break that. If you approach the nanowire by the tip and give a short pulse of on it, then it's kind of glued to the tip of the nanowire. And what you can do then is that. And just remember, it's a single crystalline nanowire. It's, I think, amazing. By doing this experiment and then a video clip of that, you can actually then calculate the mechanical properties of these nanowires. Please take care to also take in mind that your tip has mechanical properties. And so what we measured actually is that the mechanical properties of these rather ideal crystals are plus minus, so within the range of the theoretical limits. So what is causing mechanical weakness? It's normally defects, stacking fault. If you have a perfect lattice crystal, then the mechanical properties could be up to the theory limit. Okay, yeah, just, it's so nice, maybe show that again. Playing like it's a crystal. So Okay, then let's give you a glimpse. So we did some experiments with VS nanowires, which were also literature discussed for stimulated emission for lasing. We measured that. I don't want to go into the details of that. But I would like to show that yes, you can have stimulated emission measured on each of these single nanowires. What is then the case is you have to think about maybe leakage, because for stimulated emission for lasing you need mirrors, okay? And the mirror here in our case is actually the gold layer we have below, because the refractive index of both of the zinc oxide and the gallium nitride is nearly the same one. And if you don't have something in between, then you have a leakage and you will not get a stimulated emission. And the very colorful images here are actually also the calculation of the modes, of the guiding modes in these nanopillars. So you have modes perpendicular, that means over the dimension, but also along of that. And that means if you are going back to this image, you see we have small variation in the length and small variation in the diameter. And that means each of these pillars has a slightly different selecting mode, a slightly different stimulated emission coming out. Of course, you can average that over large numbers, and you get an average of that. But we did it here, prepared nanowires far away from each other so that we were able to measure single nanowires for stimulated emission. That means looking into could we do nanolasers out of that. Okay. There is some confusion in the literature, and that's why I put it actually that in. So if you measure these luminescence for zinc oxide, and it's also the case for other oxide, there are two luminescences which you have. One is coming out from defect states, and the other is coming out from near bandgap emission. And there's very often the statement in paper that if the ratio of the near bandgap emission to the defect emission is rather high, you get a high peak in the near band emission, then the quality of your wire is good. That's not the case. Have a look. Okay. So yeah, I still have my computer, so I can talk still. So what you can do is, and that is the experiment we did here, we used these wires, and what we did is then we did a measurement simply changing the power density of the excitation of these nanowires. And by changing the power density, that means higher and higher power density, and that means we simply changed then the ratio about that, and the reason behind that is there's different physics behind. One scale is linear, the other quadratic, so you can change that as you want. Okay. So let me come to another topic of if you're working in nano, you have to think about doping. If you want to make devices, you have to think how to dope these nanowires to get a PN structure. And then you end up again with a lot of things to think about. Diffusion, self-purification, surface to volume ratio. Do I have something like quantum confinement? On the left-hand side, you see a sketch. If you do a doping inside of a bulk structure, then your doping level is near the conduction band. If you now change by quantum confinement, if you now change the size of the structure, you are increasing the band gap. But the level of your dopant is the same. That means the ionization energy you need for that is actually increasing. That's one of the things. The second thing is, just imagine you have these dopants and you have to kind of you have implantation, you have these dopants in your source and drain, and then you have to activate them. And that's normally done by an activation temperature of 1050, for instance, for some micro or millisecond. Think about how far a dopant can diffuse. It should be in a lattice place, and if you're not taking care to think about that, your device might not working at all. So, to give you another glimpse, so I'm working for doping more or less in the nano crystal range, which is a very limit, so 5 nanometer. I already mentioned the increase of the ionization energies. The other effect is the question where is this dopant and what happens. It could be that the formation energy of these point effects of putting these dopants into a lattice position for these small objects is increasing. You see it here in some calculations for nanocrystals. And if you do this doping, which is very often done in literature for the nanowires, you are also changing something. So how to dope a nanowire during the growth? You have this liquid droplet where you feed your materials in to have an alloy, and then it's pushing out and growing the nanowire. What happens if I put now an additional atom, sort of an atom into this? You're changing the alloy concentration, and with that you're changing the surface energy. That means your droplet might be more de-wetted or more wetting your wire, that you're changing the size of the wire which goes there. And what you also see, and that's shown in literature, is that you're getting not a uniform radial doping profile anymore. So, and that gives you some problems, of course, then for having devices in a good way. So the challenging aspects in nanowire doping based on this VLS process is the influence of the doping materials on your growth rate. It's also affecting that. On the wire dimension, on the radial gradient of the dopant in the droplet, but also then how it's pushed out. You have an inhomogeneous radial and axial distribution of the dopants. And it's also statistic. If you go for these nanocrystals, to just give you an idea, if you have a nanocrystal, and I'm doing this in silicon, and this nanocrystal is 5 nanometer, let's make it simple, a cube of 5 nanometer, then what you see is you have one dopant, and that's already 10 to the 19. That would be metallic for bulk, and here you have even then the effect. For bulk, the ionization energy would drastically go down. Here it goes up. So there's a lot of things which still needs to be solved. There's a lot of interesting physics. It's a lot of things for devices. Huge progress in doping is done already, but I think there's still a lot our students and our postdocs can do. Let's go now to another wafer scale lithography, which is phase shift lithography that you can do on 4-inch wafers. It's a very simple process. If you have a clean room and then UV exposure there, simply prepare a mask profile as you see here with a step, then make a flooding exposure, and at the edge of the steps you're getting an overexposure. You can use that on your resist. 1-time exposure gives you line, 2-time exposure gives you dots, and that you can use then for these growth of nanowires or nanowalls. We did that in 2 ways. We did that for etching. We did that for growth of the nanowire. I show you 2 of the examples. I don't want to go into the details here. One is a silicon etched and one is grown of zinc oxide. What you're seeing is it can be done on growth on large scale. For the growth, you have to optimize it. It's not completely optimized here. We can do it better. For the silicon etched ones, the fitting of the diameter to the etched one is better. For the grown one, we have again the shift to larger size for the nanowires, but you can do that on large scale, and then you can use that for a number of things. You can go for diodes, that's etched silicon nanowires overgrown by ALD, and then have some devices here. Okay, let's go to another way. We found actually using maybe for sensors, it would be much better instead of the nanowire to use what I call nanowire. And they're using these lithography things. They're rather cheap and reliable way to grow these nanowires. So what you need is, again, such an exposure, such an use is kind of lithography, this phase shift lithography, what we have here. And then we have two processes here. One is we prepared first a layer of zinc oxide by our ALD system, and the second one is we prepared a resist line pattern, and then we were overgrown that by ALD. ALD has an advantage, you can do that at low temperature, and that means you can even overgrow a resist line, and then you do an etching of the top a little bit, and then remove the resist and have these nanolines. Let's show the mechanical properties and how that looks like. So we are trying to functionalize that. So the ALD overgrown structure of the resist results in a higher aspect ratio, and then you can look for mechanical properties of these and do testing of of these lines and functionalize that then more. Okay, let me summarize some of the challenges you have for nanosensors. Because I think it's very important to think first what you are doing before you are starting to do. If you go for a nanosensor which is based on diffusion, then normally random diffusion driven means you have a concentration gradient. And for these nanosensors, you want to go to very ultra-low things, diluted solution. So just to give you an idea, if you have a femtomolar solution, it means you have one target molecule in a nanoliter. So think about what you are saying to the one supplying you the money for your startup or for your company, or for your funding. There was just a big scandal in US which was coming out in this year. So this Theranos company, founded in 2003, got 100 million and even more, I think, and it's closed now. They claim to have tests that requires only 100 or 1,000 of the amount of blood of ordinary tests needed, and now they're indicted to wire fraud, conspiracy, and are up to 20 years of jail. So think about what you're doing. If you do nanosensors on these extremely low concentration, you might have a number of defects which are competing for dominance. It would help to do some simulation, some institutive knowledge. So there's a paper which I cite here where they are giving a lot of advice, so that's why I was putting it in. I also put it in my own advice. So what you have to do is you have to decide what kind of flow channel. These nanolines which we have could be used as flow channels. That's why I was going actually then for these devices. So then you have to think about feeding target molecules to the sensor surface. How long does it need? Reaction limited, diffusion limited, rapid collection, retention, full retention. So you have to think about that. And you could, of course, accelerate the mass transport to your surface by steering, mixing, or withdraw of some of the layers. You have to cope with charges, and charges these electrostatic interaction can enhance the bonding, current can alter the mass flow, and so on. A clever using of single molecule experiment can also enhance your bonding. So if you go for sensors for extreme size and concentration, fundamental physical limits are approached. That's one point. We can kind of overcome some of them by understanding and clever experiments. But just to give you some ideas from literature about, you want to have a nanosensor which maybe has a time of 100 nanometer, and this paper here actually compares different ideas discussed in literature: nanospheres, nanowire, a single film FAT. Yes, of course, you can go to extreme low concentration, but you might pay the price in time. Okay, and it should be, for a reasonable sensor, it should be a reasonable time to get your molecules, your single molecules, to your sensor surface, to have an electrical changing signal there. So there's a trade-off between settling time and detection concentration, and sometimes it's better to stick to a little bit larger scale. Okay, so let's go for this nano wall fabrication things. I had a discussion with one, so that's why you can change actually properties, the electric properties of the ALD film by temperature. So I was putting that in based on the discussion I had yesterday. So let me give you now some examples for drug delivery. So we had a cooperation with Bayer. So we were looking for antibiotics in farming. And by doing that, you need, if you want to go that on place with the farming, you need to discuss, you need to go there and you need to do that. And one of these clever tricks is use DNA, functionalize your surface, use a specific receptor molecule which catches the antibiotics, and you're speeding up these kind of times. And so the idea is a kind of a biology switch which you have. Small molecules are induced switching of proteins. So what you're doing, I'm showing it here. So you have a kind of an device with a gate, where the gate is a liquid gate, and you're adding there the DNA, you're adding there these molecules, and then if the antibiotic molecule comes, it catches there, and then it releases both of them, and by doing them, you're changing the charge on your gate, and by doing that, you see now the light on here. That means you have a signal. Okay. So we did that, and you have to, because it's zinc oxide, what we did, so we have, and zinc oxide is very often in kind of electrochemical things not stable, so we put some aluminum oxide on top of that. You're changing then by changing, you're modulating the surface charge there, you have a bending, and so you can release that. And so what we were able to do in these experiments was actually to trace these antibiotics below the European limit. And then I was telling my students, let's go to the extreme. Let's take a real sample. And so I was going to a biofarmer in Freiburg, and we took this milk, tested it first that there was no antibiotic in, then we spiked it, of course it was again diluted, and then we were able to measure that. And I think I have to look at the time a little bit, so I cannot go into all of the details. So we also have other devices based on nanowires, so that is a tin oxide nanowire here. What you also have to take care is, if you do these attaching and molecules attaching to the surface, having these so-called catching molecules there. There might be spaces in between. There are other things which you have in your solution might go there and also causing some charges and then changing your behavior. So you have to do it step by step in this way, and then do it in a reliable way and understanding what you're doing. And one of the crucial points is actually also the kind of contacting these wires and avoiding that something, there's a leakage current there. Okay, so we did that with nanowires, with tin oxide nanowires, and maybe I go to that image here. We use these tin oxide nanowires here in an experiment which you see on the left-hand side as a biosensor. We have other things which we did partly as control experiments. So we started actually with thin film, ALD-grown thin films in the middle. That is the middle one, and the other one is a kind of a control experiment for the influence of the aluminum oxide, which we put it over these nanowires. You are ending up also with some problems. So if you have these atomic thin layers, if it's 10 or 20 nanometer, and a rather aggressive environment, so you have to think about how long is it stable in your environment. And so the aluminum oxide which we were growing over the zinc oxide and which we needed there for the bonding was grown at 100 Celsius. So we found that an annealing step could kind of densify these aluminum oxide, giving a better result. And so we used then these additional annealing to make our sensor much more stable, to make them much more reliable in this aggressive environment, and then measured the pH value for these nano devices then in a very controlled way. And also we are looking for the glucose detection then in a controlled way. And I think at this time I have to stop somehow and summarize what we did. So I think I showed you that going to nanomaterials is quite challenging. It's a lot of fun, I have to say. You still have to think about, should I do it by bottom up or top down? Both have advantage and disadvantage. You have to control size, position of the nanomaterials. It should be reliable and cheap. If you go down to very small sizes, you have to think about how small should it be. It might be better to stick a little bit larger. Reliable electrical contacts is still an issue. At the beginning, of course, of what we did, let's say 1 out of 10 contacts were correct. Now we are better, but it's also a learning process for all of these things. Doping issue is an important, for decreasing size, you have an increasing activation energy, you have diffusion, you have statistics. Stability of these nanosensors in electrolyte solution is still an issue, and of course mass production of nano devices with high throughput, low cost. So we did it not only these nanowires for this ultra thin films, we did it also on flexible results. I didn't show that. All of that is, I think, we still have very exciting basic and applied research in future. I would like to acknowledge my members of my groups, various co-workers and fundings, and just give you a glimpse of, again, some nice things. That's our competition for Christmas cards. So if you have then something which is not really what you want, it might still be useful for Christmas. Thanks for your attention.